lot of uh, information out there, we don't always see this connection between artificial neural nets and 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 statistics. Though it was indeed, used to be called or is still called statistical learning, and because the applications have become so diversified that it has now got more and more tightly connected to applications. So when people say that you are doing image processing, they say, okay, you're using a convolution neural network. If you're using some kind of a time series models, in my last class I had discussed about time series models. Let me stop my video. Then we are talking about recurrent neural nets, or these days we talk about LSTM neural nets, long short-term memory neural nets. So the neural net itself has got very tightly connected with applications, and these applications have now gone beyond engineering. In fact, it has really flourished when applications have gone beyond engineering, and that is where the power of neural nets has really been unleashed. A challenge for engineers is how well can you adapt or adopt these methods in our applications, and that is a challenge. So one of the reasons that it became very popular is after there was a software called AlphaGo, which beat the world champion consistently in this game of Go. After that event, it was a world championship event, this ANNs got, the people, because it's black box. So once it's a black box, you're not sure what is going on. Okay. And if you're not sure what is going on, you may rather not have to deal with it. But after it beat the world champion and ANN, it was decided, people started looking at it again. And so there was a lot of excitement, which is still there. And there is software, and there is, it's gone into deep neural nets. So in today's class now, I'll try to give you some introduction. Again, I'll try to connect it to statistics because the foundations are still there. But of course, many of us today have become users of neural networks. And in user of a neural network means that you have your data, and just like we looked at time series, ARX, RMAX models, their software, and the software will generate for you the model. And so the same thing is true here. We call it training, but it is quite similar. Okay, so let me go to my first slide. So what is an ANN and what does ANN do? So ANN is a nonlinear, it does two basic examples, or it does two basic applications, and these are some things that you have already looked at. One is regression, okay, and the other is classification. And it turns out that almost any problem can be broken down or classified, categorized into one of these two. If you're using an ANN, the first question you can ask yourself is, are you using a regression problem or is it a classification problem? In our various topics that you covered, we were thinking of these as two separate entities. And it turns out they're not really different. A regression and a classification is very, very similar. Okay. It's only the level of granularity that we talk about. So, for example, let me show you this example over here. We thought of classification, regression as you have Y and you have X, and you have some function. Okay, so for each X there is a Y. So you would say, give me that function F which maps X to its image in Y. Okay, and it is continuous. then it becomes regression. But what if I broke this into classes and I said, this is class 1, okay, and this is class 2. I don't, care so much about that granularity. For example, something is low. For example, something is high. So there are two different classes, low and high. So in this way, you see that regression problem can be thought of as a classification problem where each value of y is a class of its own and they are contiguous. Okay, so many such classes. You can now think of a regression problem as a classification problem. So in a regression problem, we uh, we we typically have a non-linear regression that is where the power of the ANN is can be really harnessed. For linear regression, it is what was done in the class. So y is equal to ax. This is linear regression. In non-linear regression, when we say non-linear, we mean non-linear in parameters. For example, if you look at Fourier series and you say y is equal to some summation of an cos of nx, okay, though x is inside this cosine, you will see that this parameter an is linearly related to that function. And if that is the case, it is not a nonlinear regression, it's a linear problem. So when we say non-linear, we mean that this an comes non-linearly in our model. Then it becomes a non-linear regression. It is the parameter which appears non-linearly in the regression, okay, and not that independent variable x. So for example, if I write y is equal to a naught plus a1 x plus a2 x square, then this can be written in the standard form, okay, where of course I'm thinking of x as my parameter and not, so let me rewrite it as theta, okay. So it can be written in this form. This is a linear regression problem. Though you have an x square here and you may have an x cube, but it's a linear regression problem. So ANNs play, are very powerful tools for nonlinear regression. They are also, very powerful tools for classification. Now, I have shown some 3 diagrams down, and you will see that there are 2 classes, the plus and the square. And you'll see that in the leftmost graph, I can draw a linear boundary. So this is known as a decision boundary. Okay. So if you have looked at logistic regression or a perceptron network, we draw a linear decision boundary. On the other hand, note that in this middle graph over here, I cannot draw a linear boundary which will separate the squares from the pluses. This is an example of a non-linear regression. And finally, I have, however, note that there is a difference. And the difference is that I can still make it separable. That means I can draw a nonlinear boundary such that the pluses and the squares are separated from each other. Yet another case, which is the case that we are mostly interested in, is that the decision boundary is inseparable. Even if there was a separable in the real scheme of things, just because of noise, because of the measurements. So note that these are measurements, okay, and these are not true values. So because of the measurements, even though this should have been here, because of noise, it got pushed over here. That is always possible, okay, and so you may not be able to draw it is linearly inseparable. And so how do we deal with such problems? So classification is a general subject. It is not related to ANNs, but ANNs can attack or provide a solution for both these problems very elegantly. So let me start now with ANN and where does it come from. So this connection is like almost like a mythology and reality, and the background is that there is some connection between a neural network and the brain, and that is shown in this slide. So a brain is made up of many neurons. They say that you have about 100 billion neurons at its max level, and after its max level, you can only go up to so as you age, your number of neurons keep on shedding. But if you see that you have a an axon, which is this primary unit. So this is a neuron. Okay, um, I might just draw. This is one neuron, and one, if I may say, this is second neuron, and two. Okay, a neuron is a central processing unit. So think of this as a CPU. All right, it gets its inputs from all these different parts. So for example, I can say input P1, P2, P3, P4, and so on. Okay, and all these inputs come inside my central processing unit. They get processed over here, and in biology they say that the neuron fires. So typically people say that if it is above a certain threshold, this neuron fires, and this information is then carried forward through the axon of that neuron N1, and that axon is connected to what these dendritic structures of the second neuron, and this is how information flows in our through our nervous system. That is to say, yeah, I think I'm back. Yeah, I think I'm back. Yeah. So, unfortunately, I'm not in IIT. I had to travel at a very short notice. So I'm connecting from my parents' home network, and it's very, very flaky. So only when you step out of your campus, you understand uh, the difference. Okay, so let me continue while the going is good. So as I was trying to tell you that you have these inputs which are coming in, they get processed, and after getting processed, they traverse through this axon, and this axon is connected to the next neuron through this synaptic junction. So this is the synaptic junction, and there is a weight over here depending on the strength of that weight. Okay, means it's like a protein. So if the binding, or it's a lot of protein over there, then a lot of this information from this neuron goes into the next neuron. Similarly, there are other neurons which are connecting over here, and so in this way the information flows. Okay, so it is an axon which carries forward information of a neuron through a synapse, which is connected to a dendrite. From that dendrite, you can it goes to the next neuron. Okay, so the question is, how can we convert this information into, and the answer is shown over here. So what I showed was, I have a neuron which is, for example, uh, n1. I'll call this as neuron 1. This is neuron n2. Okay, this neuron has its input. So there was, for example, I've shown it as X over here. And so you have this on, which I might show schematically over here. So this is the axon to which that yeah, okay. So I'll probably just say this again, that this is the input X. It gets weighted by the synaptic junction W. We add a bias, so you get WX plus B. This goes into that thresholding function, which is F. So this is the CPU which applies this F, and from here it might fire or it may not fire. And so what you get, therefore, is that it goes into another neuron, and this becomes an input through another W, the weight of another neuron, and it then goes, so if I can call this as W1 for neuron 1, so this will be W2 for neuron 2. And so whatever is the output over here gets weighted, and we add this B, and then it goes into the central processing unit of the next neuron. So in this way, the information flows. So that is captured by this over here, that we say that we have a neuron where you have an input X, you have W1X plus B1. That neuron then fires through F1, and then there is a weight which is outside, so that you can have these different layers of neurons. Okay, and I'll come to that in a little bit. Now, what you do get is therefore that you have an equation of this type. Okay, and this is the basic building block of an ANN. So let me just move forward and look at it a little more formally. So I have over here a neuron. This is the input P. It gets, so what you get here is WP plus B, and this is often known as the net, okay, or the net input to that CPU. So if there are multiple inputs, it will sum them up together. So this is the summer. All right, and then it goes through this thresholding function F, and you get the output of that neuron. So this is one single neuron, just one neuron. So if your W was 2, your P was 3, and your B was minus 1, then the output of that neuron is just WP plus B, which is 5. And so it is whatever is this function, the thresholding function F. So, very common thresholding functions are, for example, logistic sigmoid, okay, log sig, as we call it. This is, it looks like an S-shaped function, okay, and it has 1 over 1 plus e to the power of minus n. Another very common popular function these days is ReLU. okay, rectified linear unit. And it just keeps, this is very, very popular in image processing, where it keeps, you have, it's always a zero, and then positive numbers are just transmitted the whatever their values are. Okay, this is known as a ReLU unit. You have a softmax function. In a softmax function is very often used for multi-category classification and so on. Okay, so this is this F over here. Okay, in biological systems, F is often binary. It is yes or no. So, and that is also used sometimes in classification. It is either 0 or 1. Okay, the neuron fires or it does not. So, okay, I have given you some inputs about the logistic, or about the different thresholding functions F of each neuron. Okay, so let me now move forward and go to the case where there are multiple inputs. In the previous neuron, I had shown you just one input. Okay, so now when there are multiple inputs, then you have many, many weights. You have W11, okay, W for the second input P2, you will have W12, okay, then you will have W13 and so on. And if so, if there are inputs, you will have this entire set of weights. So although there is one neuron, but there are many inputs, these different inputs could be coming from different neurons. Okay, and this then gets summed. So what you get therefore is W11P1 plus W12P2 plus W1RPR plus B. Okay, and so what, and so we often use this vector matrix notation, and you can think of the vector as elements of these elements of this particular weight matrix, and that gives you the net. The net therefore of each neuron is always a scalar, and that goes through this thresholding function whose examples we just saw. Okay, that is a single neuron but multiple inputs. So you can make use of the vector matrix notation. You say, okay, I have R inputs, so my weight matrix will be 1 cross R. The bias is simply a scalar because W into P is 1 cross 1. If you look over here, it is 1 cross R into R cross 1, so it is 1 cross 1. And so if you're going to add B to it, it has to have the same size, and that is a scalar. Then this net is a scalar, and then it goes through this thresholding function. So instead of showing, because you can very easily realize that drawing such kind of diagrams will become very difficult, and so you can use some kind of a vector matrix notation in the drawing itself. All right, so let me now go from a single neuron to a layer of neurons. Okay, so this is what you saw was a single neuron. So when you look at a summer and one thresholding function F, it's a single neuron. Okay, but those inputs could also go into a layer of neurons. So here I am showing you a layer of neurons. And in this layer of neurons, I can see, so there are R inputs as over here. And this is what we call as fully connected. The reason we say it is fully connected is because each input goes to each neuron. Okay. In most codes, and if you have certain reason to believe, you can decide not to put this over here. For example, if you have some reason to believe that this is an a priori information, you can knock out some of these connections. But this is a fully connected neural network. So you can see that this summer of this neuron gives you an net N1, which then goes through a thresholding function F, and you get an output shown over here as A1. So this is my neuron, right? What I had drawn before would be this. But now those same inputs go to different neurons, and what you therefore get is number of outputs. So here there are R inputs, there are S neurons, and so there are S outputs because each output, okay? So the weight matrix from being now a row vector has become a full-blown matrix. Okay, so it is an S cross R. S are the number of outputs, and R are the number of inputs to that layer. Okay, So this becomes a layer of neurons. So I should have said a layer of neurons. So what did we do? We started with a understanding, a biological understanding. We developed it into a neuron, a mathematical understanding of a neuron with one input. Then we said neurons with multiple inputs. Then we said multiple neurons, like on this slide, and that gives us a layer of neurons. Okay, we could also go ahead and write it in a vector matrix notation. And so W is S cross R. The inputs are always going to be a column vector, so it's R cross 1. There are many biases because you had S neuron. Each neuron has a bias, so it is S cross 1. You get the net, and then you get the output. And this is your thresholding function. So, if your inputs are R, let's say 4, and your number of neurons are 10, then you will call this a 410 ANN. By saying that, I can easily understand what is this neural network architecture. I know that there is the first one is the input layer, and there is one single layer of neurons with 10 neurons. Okay, so let's move forward and let's convert this to a layer of neurons. So now we had this output. You've already seen this. Okay, we had shown this one layer of neurons. Now the idea is that can you now take these outputs and connect them to a next set of neurons, okay, or next layer. So what I have therefore is a new layer, and the outputs of the first layer have become the inputs to my second layer. All right, and so I can say that these are so this should have been S. Okay, so I can call this as S1. So this is an R inputs, S1 neurons in the first layer, S2 neurons in the second layer. So this is an R, S1, S2, ANN. Okay, and the operation of the second layer is exactly same as the operation in the first layer. So now you can imagine that very easily you can build a number of layers. Okay, and this is what people say a deep neural network. So, for example, in image processing, people use neural networks with 10, 10 layers of neurons, okay, or 20 layers of neurons. And use of this deep process or deep ANN have become really very popular in computer vision and in um, for example, when you want to do speech recognition or speech processing, I won't say or text processing, rather than speech, let me say it's text processing. For example, you will see that there is a blog site and people have commented, and now the machine does not know what those comments mean. But for when I read those comments, I can understand whether the feedback was good or the feedback was bad. So a person just says something in natural language, okay? And you want a machine to tell whether the sentiment is positive or whether the sentiment is negative. So, for example, in e-commerce, you're launching a product, people comment, they just comment, they don't want to go and choose 1 to 10, right? They just write what they want. And when that happens, then whether so there are ANNs which will tell you whether the comment was positive or negative. Okay. So such kind of speech, natural speech process or natural language processing, rather image processing, which has become very important in e-commerce, are extremely popular applications of ANN. Okay, so I've just told you this: R, S1, S2, ANN. Okay, so also, these ANNs that I discussed with you now were all feed-forward ANN. So you see, I had an input, and it went into a black box and it gave me an output. This is my ANN. Okay. But we have looked at time series models. And when we looked at time series models, we said that Y is a function of T. It evolves with time. Okay. And so the question is whether we can take the initial condition. So if this is Y of T, whether we can take Y of T minus 1, the other inputs, just like in an ARX model, okay, and model this as a model of a dynamic system. Such neural networks are known, in fact, they are NARX models, non-linear ARX models. Okay, and that is also something that can be implemented. Or you could take that output, so I could have had a y of t, and like in a true differential equation, I take that same input or output and I feed it back after a delay unit. Okay, so it is y of t is equal to a1 times y of t minus 1. See, note that this no is very different from the previous slide where it was y of t is equal to a1 times some approximation of t minus 1. See, this is the same variable. Okay, it's purely recurrent. And that is what you can do using a recurrent ANN. Now, let me move forward and I will go to some aspects of how do you use a neural network. So what I've covered so far is the architecture of a neural network. And now I will try to move into, how does one use these neural networks and so on. So essentially, the input P that we looked at. So if you have your input layer, so this is an input layer, okay? Then you have your first layer, you have your second layer, and this is, let's say you have a third layer, and this is your output, okay? So these inputs now are called features. And this is where, I will say that there are two schools of thought that one school of thought says that, features means domain knowledge. I need to understand what is the problem I'm solving and then choose what is X. Okay. Um, there's another school of thought which says that, you just give me all possible inputs that you have. I mean, don't bother to tell me whether there is a connection or there is no connection. And what we see nowadays being called as feature engineering. And they say we will do this pre-processing step ourselves without, domain knowledge. So feature extraction, if you will, or feature engineering, as it is often called. So that gives me what is this over here, the first set over here. Okay. So in some sense, in convolution neural networks used for image processing, they just give the image. They give pixel by pixel values of the intensity, and the starting layers do nothing but some kind of feature engineering. The beginning layers. Um, but in most engineering problems, no, you will have to intervene and do feature engineering in some way. Now, one way is, of course, PCA. You have all seen principal component analysis, and a very common way of doing feature extraction is by actually taking your data X and finding out the dominant components. So if I call those principal directions as V1, V2, let's say V1 and V2 explain more than 95% of the variance, then instead of giving, let's say this was X1 to X50, and then you have just two features, V1 and V2, and you find out that they explain 95% of the variance, then instead of giving X1 to X50 as 50 inputs, you can just give two inputs, V1 and V2. It'll, as you can now imagine, your weight vectors will become smaller in size, and that might be beneficial. So, in modeling, we use one term called Occam's razor. And Occam's razor says that, if you can explain observations through different hypotheses, then the hypothesis which is the simplest is probably the truth. Okay. Um, so if you can explain the same information using just two or a smaller neural network, then that probably is the truth. Though we saw in Leung's comment that it is only the utility of this tool which is of interest to us and not the pursuit of truth. Okay. So so it helps to do this feature extraction not only for the fact that we are not pursuing truth but just utility, but at the same time it helps numerically. The demand on the amount of data needed drops as the number of parameters, that is the weights and the biases of that neural network drops. So there is some utilitarian reason to do feature extraction just so that you can get a better neural net with lower number of data, with lesser number of data. All right. So let's take a look at what are the inputs and outputs. So n data points. So you have n targets. So the output in your training set is known as the target. That is what you are trying your neural network to be able to emulate. And you have candidate inputs. Okay. So you should be able to decide. So I have written here P, and P very often comes because inputs, are thought of as prototypes. So you have your prototype where you have P1 is a vector and Pn is the last example or prototype. Okay. Corresponding to this are the targets like shown over here. Okay. And the target need not be scalar. It could be, number of neurons. So one thing will be very clear, that the number of neurons in the last layer should correspond to the size of the target. So if the target is just one, then the neuron, because that is my output of the neural network. If my targets are five, then I should have five neurons in the last layer. Okay. So that gets determined, is not the choice of a designer, but just gets determined by this P. Okay. So if, for example, if I have to give you an example, let us say I look at the temperature of the day, the humidity of the day, the time of the day, okay, and I'm trying to predict whether it will rain tomorrow, and let's say whether it will be hot or not so hot tomorrow. So there can be two outputs. So if there are two outputs, I will have to have two neurons in the outermost layer. Okay. Now, of course, you have your training set. So you have all these examples and you have your targets, which get fed to the neural network. So this becomes your, which goes into that ANN. So very often, people will scale the data. They might make it zero mean unity standard deviation, or they might do this -1 to 1 scaling. So some kind of a scaling, because the temperature might be in different units, humidity might be in different units, the time might be in different units, and it makes sense to be able to scale the data before you use it. So if you use principal components, it gets auto-scaled. It becomes zero mean unity standard deviation before you apply. So, it gets auto-scaled. But some kind of scaling is desirable. Okay. So now that we have seen what an ANN looks like, we have seen how the input data should be given to the ANN. Let's see as to how are these ANN obtained. Or, obtaining an ANN now essentially means finding out all those weights and biases. So if I had weight vectors in each layer as W1, B1, okay, then I have W2, B2, and so on. And let's say my last S, so I have WS and BS. So training means given the data. So just like in all our exercises, given data, and if I might call data as D, the question is, how do you obtain these weights and biases? The moment you give me those weights and biases, I'm done, right? So, uh, you know, one of the most popular algorithms is known as the backpropagation algorithm. And the backpropagation algorithm is essentially it's nonlinear optimization. So it is like this, that if I give you, let me try to write down the output of the neural network y. Let's say it's a 3 So it is the third thresholding function. So it is F3 into, and I'm finding it difficult to write. So it is, so there'll be weights, W1. No, so there might be a weight outside. Nah, I'm getting confused in writing it. If you try to write down, so we've looked at the architecture. So it should be possible to just write down. Okay, this is P. Now this becomes WP plus B. Now it goes through F1. Now this F1, and there are many other neurons. They go through F2 and F3 and so on. If you write it down, you will see that this becomes a very, very complex uh, uh, equation. Okay. And the weights, as I told you right in the beginning, are inside these thresholding functions. And these thresholding functions are always nonlinear. We don't use a linear thresholding function. If you use a linear thresholding function, it becomes equivalent to linear regression. And you can always find an equivalent regression problem, which will give you identical results. So what I was trying to show you is that these weights are inside these, and these are now, these are composite functions. So you are cycling through functions, so it gets transformed by F2, and then it gets multiplied, then it gets transformed by F3, and so on. So there is a lot of non-linearity in this, and so it becomes a non-linear regression. Okay, so and how do you solve non-linear regression problems? So you can use some simple method like steepest descent or some Newton based method. So backpropagation algorithm is actually using a nonlinear optimization to find these different weights and biases, okay, but in a very elegant way, okay. And uh, so if you now an ANN, for example, shown over here, there are really two steps. In the first step, you take your P and you propagate it forward. So this is the forward propagation step, and you come here. So let's say you had given P1 and you get A2 output of the second layer and the first corresponding to P1. Now when you come here, okay, let me put a parenthesis here to indicate that it is output and not a square. But what you wanted was really T1, okay? Now, because these weights and biases are not trained, so you don't get T1, you get A1. You're not very happy, so you define an error. And the error, so there are two very popular ways of quantifying it. And one is known as the mean square error, okay? And there is also something known as a cross entropy error, okay, or cross entropy uh, objective function. So in either case, so for example, a mean square error will be T1 minus A21, the whole square. So if you look at a steepest descent algorithm, it will tell you, okay, look at any weight W star. Then W star is equal to W star old minus some learning rate alpha times del of this MSE, mean square error, okay, by del W star evaluated at old. This is a steepest descent step. It tells me that the new value of the weight is equal to the old value, and you subtract, you go in the direction of the steepest descent, because the moment you go in this direction, this MSE will come down. Okay, it will reduce in its value. And that becomes is a backpropagation algorithm. So where is that elegance? So you say, okay, this is a very straightforward, well-known method. The elegance comes in the fact that in the backpropagation algorithm, this error is backpropagated, or the sensitivities of the error. So first we calculate del MSE by del W for weights of the second layer, okay, and then so this is a sensitivity, some sense, okay, it is a sensitivity, and this sensitivity is then back propagated, and then you come back, and then you are able to find out uh, uh, with respect to the first layers, and the moment you have all of these, you can start plugging them here and getting this new value of the weight. So this is the backpropagation algorithm. It essentially takes an input, propagates it forward, comes to your output, compares the output with the target value, looks at what is the objective function, and if the objective function, for example, is mean square error, it then back propagates the weights all the way to the first layer, and in so doing, it calculates all these different um, different gradients which are needed in this gradient-based optimization. Okay, so was essentially the backpropagation algorithm. And as I told you, although I didn't describe what a sensitivity is exactly, but the sensitivities of the error to the network parameters are backpropagated. So, of course, the issue is that the target is noisy. So this target value has noise in it. So T is equal to T true plus some epsilon noise. Okay, and so we don't want, so while we are fitting to be able to approximate the target, we remember that this is noisy, and so we hope that we don't overfit and get this noise also. That means we don't have so many parameters, or we have parameters, they don't try to fit the noise, and that goes back. And I think I have a slide subsequently which describes that. Okay, so that is the backpropagation algorithm. So again, if you want to look at it from a statistics point of view, then when you're using mean square error, the mean square error comes when you have a likelihood function. So it's a frequentist approach. And when you assume that your distribution of your observations is Gaussian, then the likelihood becomes the maximizing the likelihood becomes minimizing the squared error. So that is the connection with statistics. Uh, so that is where this cross entropy objective function becomes useful. So very often in classification, it does not make sense that things are distributed in terms of a Gaussian distribution, that my targets have a Gaussian distribution. You might have a 1 or a 0. Okay. And so this cross entropy says, okay, my distribution is not Gaussian, but my targets have a distribution of a are Bernoulli trials. Okay. And if you do that and you go through the same process of finding the maximum likelihood, you don't get mean square error. You get a slightly different function, which is known as the cross entropy. Okay, so what I have finished with you is what is an ANN, the architecture of ANN. We have also looked at what is this training data, and we have looked at, at least a very, um, uh, at a very, what should I say, um, at a very high level, we've looked at how training happens. And so the moment you see that it is connected, a lot of people will ask, others who work in ANN and who themselves don't work in ANN. So tell me, is ANN eventually fitting? Okay. And actually the answer is yes. Okay. But it's a more elegant way of fitting. And it's also a more elegant way of building that machine. Okay. So it's a, so as you know, this comes as part of machine learning. And why is it machine learning? It is because you can think of the ANN as machine. You have given it a data set, and without you intervening, okay, it will be able to learn those weights and biases through that fitting procedure. And so it is machine learning, as it is often called. Now, um, another issue, which always comes in ANNs is overfitting. Indeed, this issue comes again in regression. So, in some sense, you see a deja vu when you look at ANN, because a lot of these things we have already looked at regression, right? So, in case of ANNs, and indeed in any regression, uh, you have a model. So you have data, if I call it by D, and then if you want, I might call my machine learning, my machine with M, and this M has parameters of weights and biases. So in training, I take this data and I try to arrive at these weights and biases, okay, using this machine. Now, one question that the modeler will always face is, what how many layers to take, how many neurons in each layer, and so on. So you know that in the first, the inputs are fixed by the problem. So if you are doing feature extraction, so it's just the number of features. And the last layer, the number of neurons equals the number of outputs. You don't have much of a choice over there. Okay, so those two parts are fixed. So your P, if I might write it here, and your last neuron, if I might say it as N, is fixed. As a designer, you have to fix what are these intermittent, how many layers, okay, and how many neurons in each layer. That is what is in your hands as a designer. So what is shown in this schematic is the following idea that, as I told you, your data is noisy. The targets have noise in it. So it could be T is equal to T true plus this noise, which I might say as epsilon. And if you have too many parameters, you have many, many layers, many, many weights, many, many biases, okay, then uh, so you can see this noisy behavior, right? So see, I might try to draw it here. So it's like this. It's very, very noisy. Oh, it goes here like this. It's very, very noisy data. So if I have too many weights and biases, then while I understand that there is a general trend which I have to capture, okay, but because you have so many parameters, it might use this extra parameters that you have in order to learn that noise. So it might say, oh, there's very interesting feature that is happening here. It's going up and down in a V. And you as a modeler say, no, 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 that's just noise, just ignore it. But if there are too many weights, it will try to use those extra weights and biases to be able to actually learn noise for you. Okay. So if this blue line, which I have now overdrawn with a red line, is your neural network output, you would say, oh, this is good. It's right. It's got my trend. But if you have too many weights and biases, it will end up trying to learn the noise structure. So while your mean square error goes down on the training set, you will find that what we call as generalization. Okay, so we say how well is your neural network able to generalize, you'll find that it becomes poor. So while the training performance is good, your generalization is poor, and that is known as overfitting. So in ANN literature, there are two popular approaches to avoid this overfitting. So the point is, one is, okay, don't take so many layers and don't take so many biases, okay, because you'll have too many parameters. But these are completely black box approaches, and we really don't know. We really don't have an idea of that how many to take. So what a modeler can do is take, a large number of weights and biases and use some approaches so that they can, so if let me say that if I have to train, so let's say this is my noisy data. My first neural network, which is untrained, might give me an output like this. As I get, better and better, it might do like this, and it might then do like this. And as you keep on training, so presenting the training data to the neural network is called as an epoch. Okay, so if there are, let's say, 10,000 data points, so presenting the 10,000 data points to the neural network is called an epoch. And and because this is non-linear regression, it's not linear regression, you will have to, and let's say it's a steepest descent problem. So you will have to present many, many epochs. So your number of epochs should be very large. So let's say after the first epoch, this is what it was. After the second epoch, it became this. After the third epoch, it was here. And as you keep on presenting it again and again, and it has this extra flexibility of parameters, this might start doing this. Then you know that, no, this is not what I wanted. I would have been happier with the third epoch. So one way to avoid this overfitting is early stopping. Stop presenting the data again and again by a method called. And the way that cross validation works is, so typically you take your data set, you split it into three parts: a training set, a validation set, and a test set. Okay. Now Now this is your objective function J. As I told you, it could be mean square error or it could be cross entropy. And these are the number of epochs. Now, if let's say you look at your mean square error, as you keep giving more and more, as you keep increasing the number of epochs, so epoch, as I told you, is presenting that data set once to that machine. Okay. So in the beginning, like the first epoch I drew on the previous slide, it will start to get better. Okay. Now, because this is optimization, and it is trying to minimize the squared error. For the training set, you will always get your your objective function will keep going down. Even as number of epochs keep increasing, that for the training set, the mean square error, so I might say MSE for the train set goes down. Okay. But so because it was the noise in this training set that further and further epochs as we advanced, the parameters try to fit and try to do that overfitting. So once they see some noise structure, they try to fit to that noise. But remember that the validation set is not used in training. So training is based only on the training set. So the noise structure in the validation set, so you remember the uncorrelated noise, we said epsilon is uncorrelated. So in the training set, it had a certain type of realizations, but it is uncorrelated and this is independent, for example. Then in the test set, there is another set of realizations. So let's say it was the same input, but in the training set, the realizations looked like this, and so this was your training data for that same thing. For your, it could have been this. So you see, there is a difference. And so while you were using the training set for finding out those weights and biases, that same weights and biases will not do well on the validation set. And so what do you find on the validation set is that when you start plotting, then the objective function comes to a minimum. And when you start overfitting noise, so this is all noise getting fitted in my training set. In my validation set, it says, oh, the performance becomes poorer because it is not able to emulate the noise in the validation set. And that is the reason, we stop training over here. So we say that it is only noise that you're learning. You're not learning any new, trend or like a correlational structure, but you're only learning the noise. So this is one way of doing, of stopping your training. Okay. So as I said, and finally, see, there might be many neural networks. So you might have trained ANN1, ANN2, and so on. In each of these, you have used the validation set to decide where you stop. Okay, so it is useful to have a third and completely independent set. So see, training set was used to reduce your mean square error. Validation was used to decide when to stop your training. So you use a completely independent set called the test set on which you report your performance. So you can report your objective function. What happened? So you report it on this test set for comparison, okay, between different ANNs. So that was the frequentist approach, okay. And something that has become very popular of late is known as Bayesian approaches in machine learning have become extremely popular. And in statistical literature, it used to be often known as regularization. And under certain conditions, the two are equivalent. So in regularization, um, in regularization, we do not divide the data. Okay, we don't have this training set, validation set, test set. In fact, what we do is we make use of a regularization theory, which for us, now that we have looked in some detail on the in statistics, is very straightforward to describe. In the frequentist approaches, we said that it was the target set which had a distribution. Okay, so we could have said it has a normal distribution. Okay, and the weights W and B were all assumed to be deterministic. It's only that they were unknown, but they were assumed to not have any uncertainty associated with them. In regularization theory, we make use of a Bayesian approach where we say not only are the targets having a distribution, also all my parameters, let me do a catch-all with theta, have a distribution. Okay. And you are free to choose the distribution. See, we looked at many different types of densities. Okay. It turns out that if you use your targets to be normal, then your likelihood is the square of the error. Okay. And it turns out that if you assume that your weights and biases also have a normal distribution, okay, then in this Bayesian approach, it turns out that the performance index is this. Okay, this is also known as, it corresponds to a maximum a posteriori estimate of your weights and biases. So minimizing this is maximizing your map estimate. Okay, maximum a posteriori estimate of that of the weights and the biases. The two are equivalent. Okay, so, and it turns out to be this case if you decide that my theta have zero mean, okay, and they have some well, I put lambda alpha here, so let me put lambda here, and they have some lambda times identity matrix as their covariance, okay. This has mean, so if I assume that the errors have covariance of beta, okay, then you can show that the maximum a posteriori estimate is nothing but you get lambda by beta, which we call as the regularization parameter. So from a statistical point of view, the regularization parameter is nothing but the ratio of the covariances of the error, or I'm sorry, the noise in your target set and of your prior. So this is known as a prior. Why is this known as a prior? Because remember, I'm trying to find out what is theta. Okay, so f of theta, this is the density. If I write it and I'm taking it as normally distributed, this is known as the prior density. And that is what I have written over here. This is the prior density. And what we try to do in maximum posteriori estimates is we find this conditional density. Given the target set t and x, what is this density? Okay. And map estimate, which is given by this, is nothing but the expectation of this of that, conditional expectation. Sorry, I should have written here as theta. So this is nothing but the conditional expectation using a conditional density. And we had seen how to find out expectations, and which easily extends to conditional densities. So this is a very different way of solving it. Here, you see, we don't divide the data. We have a performance index which, under certain assumptions of the prior and the observations, gives us this objective function, which corresponds to maximizing this mean, the conditional mean. Okay. Now you will see that there is a very if I choose alpha as infinity, okay, as alpha goes towards infinity, you will tell me you don't need to solve this. I will tell you the answer is all the weights and biases should be set to 0. Okay, and as alpha goes towards 0, it is nothing but you go back to the frequentist approach, okay, which is what we had seen before. And so that will have all problems of noise, overfitting and all. So frequentist approaches, when alpha is 0, have this overfitting problem. And so conditional expectations, I'm sorry, the regularization is, the cross validation is one way of avoiding that overfitting. Okay, but it is well known that all frequentist approaches have an overfitting issue, and that you can avoid by taking a Bayesian approach, which is known as regularization in ANN literature and even in statistics. Okay, so alpha, therefore you have to choose alpha. Now you'll see that there is a new aspect which is there, and that is that I have all these new parameters which are coming into play. So which I have to now choose. I have to choose what is this regularization parameter alpha, Okay, or if you were doing it in a Bayesian setting, you would say, oh, I need to find out what is the variance of my weight prior, lambda, and so on. Okay, these parameters which come into play in Bayesian approaches are known as hyperparameters, because these are not weights and biases that are used in the model, right? I mean, eventually when I get my ANN, I will not be using these weights and these hyperparameters. I will only need weights and biases. But these parameters are needed to be fixed before we can do any work, and these are known as hyperparameters. So one of very areas of research is doing hyperparameter tuning. How do you choose? Because you will see that if you choose different values of alpha, you will get different weights, and these weights and your performance of the network will change. So nowadays you also have software which tries to do optimization of those hyperparameters as well. Okay, so there are so many applications. I have limited my slide to only engineering type of applications. You will note that I've also written system identification, or that is time series as one of it. To give you very briefly an example of an ANN, where you were trying to predict. So this is an atmospheric distillation column, and you were trying to predict. So out of the many products that you have, one is kerosene, and you want to predict the ASTM 95% temperature of kerosene. So this is nothing but a quality measurement. So this is an example, another example of soft sensor. Okay. So I don't know whether I should say it's a conundrum, but you will note one thing, that in engineering, everything which is of great interest to you, for example, a quality, is very difficult to measure. Okay, is very expensive to measure, and everything which is not of direct interest to you, it's only of indirect interest. Okay, is very easy to measure. For example, quality is the key measurement that you would like, and a temperature or pressure of the distillation column, or the or of the side columns, is not of direct interest. Okay, and that is cheap to have. So soft sensors essentially try to take uh, easy to measure variables and predict the difficult to measure variables. So for example, if you have a batch reactor, it's only at the end of the batch that you can take a sample, run to your lab, and get some measurements. There'll be a lot of downtime, okay? Or even in case of this continuous atmospheric distillation column, you will have to take the sample, go to the lab. You need to have online quality measurements, okay? So for example, you can use a online gas chromatography setup. I've now yeah, Prakash, Om Prakash, I've got trained my, to figuring out when I am not in the meeting. So I had stopped discussing when I noticed that. So as I said, um, how to use this easy to measure measurements, okay? And then so we had 546 n the number of measurements, and we had 59 of these. So the first thing was feature engineering, and the feature engineering meant pre-processing, and we came up with a few of these out of those 59 that we will use as input in our ANN. And so we have used things like correlation coefficients, partial correlation coefficients. I will suggest very heavily that you should try to do a principal component analysis and try to find out what are the principal components. And as I was trying to tell you that, there are people who say, you don't have to give me any domain knowledge. So they have these bag of features, as they call them. And this bag of features could be anything. They would just take, for example, the mean, the median, the range of the data, the extreme values of the data. So any kind of statistic that is what they try to throw at it. So you have a bag of features or a bag of words, sometimes they call it. Okay, and and they try to decide. Now here, a more engineering kind of an approach was taken, where some simple measures were used to find out what would be the interesting inputs. Okay. Also, for example, there is something called Mello's C sub p statistic, and we use that to be able to find out what will be the set of features that go in, and you have to, some judgment was made. I will skip this because it's not of direct interest. We thought that fundamentally there is one property called gap overlap, which then critically decides what is the ASTM 95%. So let's predict that gap overlap first, and then predict this 95% temperature. So because this gap overlap is also is not an observable, it's only in a campaign mode that we had values of gap and overlap. Okay, or just take a really data driven approach and you say no, take the inputs that you had here, okay, take these inputs, merge them all together and make a single neural this, okay, and to predict this ASTM 95% temperature. That this was done with one hidden layer. This work was done in 2001. So uh, still it was not felt that you could really go to large number of layers like it is being done these days, and different number of neurons were tried, and some mean square prediction error was around 2.9, which was the best that was obtained. So finally, the neural network. So you see there were 8 inputs over here. So this is 8. Then there were 5 neurons in the hidden layer, and there was 1 neuron in the output layer. So it was an 851 neural network. This used the log sig function, so which is 1 over 1 plus e to the power of minus n. And these are those net values coming from each neuron. So and I think I've knocked out the figure, but essentially when you want to now apply it at the refinery, these are the different. So firstly, I had uh, done scaling of the inputs. So these scale factors have to be remembered, right? And whatever they were, because I had scaled, because whenever I'm going to use that neural network, I'll have to use the same scale factors in order to move forward. So I'll need to scale it. And then I have the weights and the biases, which were obtained. Okay. This was using without regularization. And so I made sure that the number of neurons is less so that I don't overfit. So when you look at that, you find that as you increase the number of neurons, 6 and 7, and these are reported on your validation set, you can see that after 2.9, it went to 3.3. So here, it's not just the epoch. So I had done cross-validation to stop at each case um, in each of these different neural networks. But yeah, so this is the test set. So on a common test set, we reported these values, and you can see that 2.9 was the best. And beyond that, it became worse again. Okay, yeah. So here was the performance of that ANN. So uh, so these slides we will share with you, and there are some more examples of uh, here. We used for dynamic. So that was a case of a steady state model. But what if you have a system of ODEs? And the example over here is that of a fermenter, a continuous fermenter. And you want to be able to learn the behavior. So of course, ODEs, because here in the previous example, there were real measurements coming from the plant. And here is a simulation plant, a simulated plant. Okay. So that's why I said my it is an ODE plant. The plant itself is not real, but just ODEs like shown over here. And you try to predict. So this is how. So it's a semi-batch fermenter, and you could try to predict how the cell mass grows with time, how the substrate depletion takes place, the protein grows with time, and of course the volume of the batch. Okay, so it's but what I wanted to tell you is that you could also model such kind of systems which are let's say using a recurrent neural net or a feed forward neural net. Okay, so let me talk to you about one more neural network. So I have, these are some, again, it is the same semi-batch. I was trying to show that this is an ANN, the red line, and the blue line is a process, and it works that input-output relationship. Let me look at the time. I have about 10 minutes more. And so let me just talk to you briefly about one more neural network, which is from a slightly different type of a category of neural networks, which are based on kernels. Okay. And it's just a three or four slide exposition, so I should be able to finish it. So a very different approach, which also emerged in the 1980s and early 90s. So, the backpropagation neural network was proposed in 1980s, okay, with that multi-layer backpropagation neural network. Now, has to do with an example is of course a radial basis function neural network. I'll just show you the difference. So unlike this log sig that we had, or any of those functions, which are more global functions, and why they are global, because they are 0 and then they become 1. So this what I plotted here is the net n, and this is the output f of n. Okay, they are global functions which have their influence far from that value of n is equal to 0. At n is equal to 0, 1 over 1 plus e to the power minus n is 0.5. Over here it is 0, not well drawn. The 0 should be somewhere here. And this will be about 1, okay, when n is very large. So there was an understanding that why don't we use what we call as local units, whose sphere of influence doesn't go well beyond, this transition from n being negative to n being positive, but are just local units. That eventually, fueled this RBF, or radial basis function neural networks, and the output of this neural network is shown below. So I have, for example, let me call this as C1 and C2, and I'll come back to you in a minute as to what are C1 and C2. So here, the local unit, in this case, I'm using a Gaussian node, is simply a Gaussian node, and so it is exponential of minus half the input, and I can call my input as P minus C, the whole square, by 2 sigma by sigma square. This is an example of a local unit. I'll just call it G of something. Okay. So you will see that this X is the input, or you can think of it as P1 and P2. That this local unit, like any Gaussian, has a center, right? That center, I'm calling it as C over here. And you have the width of this unit, which is sigma. Now, P is a multivariable, or the input is multivariate, which means that, it should be a multivariate Gaussian. But, we don't use a multivariate Gaussian, but we use a radial basis. So, you may remember that if I had a multivariates like P1 and P2, then these Gaussians, depending on this matrix, will have some kind of an orientation. But by making sure that this variance is simply sigma square I. These have all become circles. So my Gaussian is now merely at this C center, they are just circles. Okay, so you can think of this Gaussian node which has this property that when the input P or X is very close to the center, it gives you an output, okay, a non-zero output. But when it is away from that center, then it just gives you a zero, because it decays very quickly, depending on what is the value of this bit that you choose. And so it's a local unit. The Gaussian unit is a local unit. Only for inputs that are close to the center, it will fire. For inputs that are far away from the center, it will not fire. Okay. Now, how does this simplify things? So truly, this C and X belong to the same input space. Okay, like I showed you over here. So if this is C over here, okay, this is C1 of this node, and X is very far away from it, there'll be no output. Because only close to C it will fire. If X was very close to it, over here it would fire. Okay, and if X is far away from it, or the input is far away from the center, then that node would not fire. So shown over here is a neural network with two nodes, single output, and you have these as your weights. All right. So it's a very simple linear combination of your weights. So I can think of this as an linear in weights. Okay, so I can write it as G1, the first node, plus W2 into G2, the second node. Okay, it's a very simple neural network. I'll give you an example of how you could design this just by inspection. An example, you have two different categories. You have 0, 0 and 1, 1, which is whose target is 1, and you have 1, 0 and 0, 1 whose target is 0. So you see, these two belong to one class, and these two belong to another class. Okay. Now immediately you will see that these are not linearly separable. You can't draw a single line where the two. Oh, I think. Am I audible?
Yes,
I have
sir.
realized that whenever a phone comes,
Yeah.
this gets the connection goes for a toss. Okay, so yeah, I think I'm back.
Yes, sir.
Yeah. So I have realized that whenever the phone rings, because this is a BSNL's connection, whenever the phone rings, the router gets disconnected. So I think for my next class, I'll just disconnect the phones. Okay. So as I was saying, no, that this is known as an exclusive OR. Okay, that 1 1 1 1 and 0 0 is one category, and 1 0 0 1 is another category. And you see that this is a simple problem when it's not linearly separable. But if I wanted an output to be 1 over here and an output t should be 1 over here, then I know that I can just put one unit over here, one Gaussian node over here, okay, and one Gaussian node over here. And I can make it thin enough that as you go away from this center, it quickly becomes 0. Okay. So if I give this output 0 0, okay, then this node will fire. This node will not fire, and you will get an output. And so if I choose my W1 to be 1, I will get an output of 1, because I had Y is equal to W1 G1 plus W2 G2. So because my G1 is now centered at 0 0, so I have chosen C1 to be 0 0, then when I give 0 0, it will fire, and I can choose this W1 to be 1. G2 will not fire because it's a local unit, it is far away from 0 0, and you will get an output of 1. So I'll choose my W1 as 1, W2 as 1, and you'll get an output as 1. If on the other hand, if I give, let us say 1 0, then neither G1 will fire nor G2 will fire, and so you'll get an output of 0. So if you give 1 0 or 0 1, you will get your targets 0, and if you give 0 0 or 1 1, you get your targets of 1. And this is the description in a three-dimensional space, that you have two nodes, one placed at 0 0 and one placed at 1 1. Okay, and they have only a local sphere of influence. So when you go to a 0 1 or a 1 0, they both of them don't fire, and you get your desired result. So that is a radial basis function network. Again, there will be issues as to how do you train it and so on. Okay, so I will skip that. But this is another very interesting radial basis network. It's called a kernel because we use these Gaussian kernels. And these G's are not these are Gaussian kernels, and they are radial. So that's why these are also known as kernel-based neural networks. So I have come to end of 1 o'clock. So I think I will stop here. We all are hungry and need to have our own training, our own what should I say, thing to come in, so we can train ourselves and get ready for the 2 o'clock hands-on session. Okay, and I figured out how to make sure that the net will not go away. So thank you, everyone. I will see you at 2 o'clock. At that time, we can